Hey, what's going on? We're working through a little bit of notes today on zeros and multiplicity. Should be a really short video. Zeros is a concept you guys already understand, and multiplicity is a new one, but it's pretty straightforward. So one thing is that we're going to talk about is how zeros relate to your even and odd degree functions. We know that the points at which the function intersect the x-axis are considered to be x-intercepts, and x-intercepts are considered to be zeros. Something that we've done several times this week is to list things that are the same as zeros. So that would be zeros. That would be x-intercepts, which are the same. That would be solutions, which are the same. That would be zeros. Sorry, we forgot zeros. That would be zeros, solutions, x-intercepts, and roots. So those four things are all the same, which means looking at graphs, zeros are x-intercepts, where they touch the x-axis. A polynomial function of degree n can have at most n real zeros. So that's a really interesting point that maybe you haven't thought about before. We've kind of said that a degree 2 polynomial will have two answers. That's the idea, right? A degree 3 polynomial could have three answers. A degree 3 polynomial could never have four, okay? And that is the idea here. If I replace, some people don't like this letter n because it seems a little too funky, but if I put 6, then it's 6. Right? So if I've got a 6-degree function, that could have at most 6 real zeros. Now 6 would be an even function, so it would look like this. And so I might have a function, if it's a 6-degree function, that looks like this, and I could have 1, 2, 3, 4, 5, 6 zeros. No way could I have 7. If I have 7, that guarantees that I'm at least an 8-degree function if my exponents are up like that. Now, of course, I've kind of lied to you again there, talking about whether I could have 7 or not, because an even degree polynomial has an even number of zeros, or perhaps has no zeros at all. And an odd degree polynomial has an odd number of zeros. So, a 6-degree polynomial could never have 7 answers because 7 is more, but it could also never have 5 because 5 is an odd number and it's a 6-degree function. So that's pretty interesting, okay? A lot of times doing these exact examples, maybe doesn't give us the clearest picture. So if I just doodle this, I know that this is odd. I know that this is positive. That means I should be going from low to high. Now, if I'm going to connect these two lines, I can go straight through. That gives me 1. Or I can go up, give me 1, get me a second 1. And you notice how there's no way for me to finish like this, right? I'm going to need to go back and connect to my top finish here. And so I have to have at least 3, right? No way can I have only 2, right? Because I can have 1, 2. I need to finish up here. And so I need to finish with a third. And that guarantees me that I've got 1, 2, 3, x-intercepts. Now, let's look at this actual graph. Let's go to Desmos. X cubed plus x squared minus 2x. All right. X cubed, can't be capital X. X cubed plus x squared minus 2x. Something like that. X cubed plus x squared minus 2x. X cubed plus x squared minus 2x. Cool. Yeah, looks pretty similar. We've got 1, 2, 3 different intercepts. Exactly how we thought. Just to draw a graph. Doesn't have to be perfect. We're moving on. Okay? We've got the next one. This is a 4-degree polynomial. So we know that this is even. We know that this is negative. Maybe I should just draw a negative sign there. That means that we need to be down, down. Now, we could have 0. We could have 1, 2. We could have 1, 2, 3, 4. But notice how there's no way we can finish on an odd, right? This is a 4-degree. So if I have 1, 2, 3, I can't look like this because we know I need to finish down. This would be a 3-degree. So I need to finish with my 4th 0. And again, our graph might look like this if we type this in. It might look simpler. It might look more complicated. I'm not going to go through the process of typing this in just because I want these to be short notes. You guys know what's going on. So this is not the exact graph of how this looks, right? This is just a guess. So moving on. What is this function in factored form? Okay, so this is something that we've already talked about this year, the relationship between factors and zeros. Okay, I need to start with a GCF of taking out an x, and I will be left over with a trinomial that I can factor with the shortcut trinomial, -2, -15. I know that's going to be x minus 5, x plus 3. Now here's my three factors. And notice how factors is not in our list of things that are the same. Zeros, x-intercept, solutions, roots, not factors, okay? So looking here, I need to take these three different factors and I need to get them into solutions. So that would be x equals 0. There's my first one. I'll use green. X minus 5 equals 0, add the 5, x equals 5. And we can use, I don't know, this color. X plus 3 equals 0, subtract the 3. So there's my three different zeros. So we need to make sure that we're comfortable that factors create zeros, but factors are not the same as zeros. If my factor is a -5, my solution is a +5. So make sure we're cool with that. There's my 3. And just like we said before, right? A 3 degree is either going to have 1 or 3. It can't have more than 3, and it can't have an even number. And so 0 is ruled out, 2 is ruled out. We're stuck with either 3 answers or only 1 answer, and we've figured it out like that. Now, we could draw the sketch of this graph. You know, if I want to go super brief here, x-intercept at 0, 5, and -3 is 0, 5, -3. Positive odd means we're going from low to high, and so our graph, boom, boom, boom. There we go. There's our graph. Now, obviously, it's not a perfect drawing, but that is a very good representation of how our graph looks. And I can double check that. X cubed minus 2x squared minus 15x. Let's see here. X cubed minus 2x squared minus 15x. Yeah, it looks like it's much more up and down than I have, but -3, 0, 5. Exactly how we thought. Odd, positive, low to high. Easy. Don't need that. Now, multiplicity is the thing that we're really talking about because all of this we already understand with zeros. Now, maybe there's a little bit of new information as far as odd functions have an odd number of zeros, but multiplicity is the only thing that's really going to be a bit spicier as we talk about it today. Now, if this is our function and we want to write this in factored form, again, you know, I'll give you a little secret. Pretty much we're always going to start with GCF if you see anything that's a cube. So we're taking out an x. We're going to have x squared minus 6x plus 9. That's going to be -3 minus 3. Multiplies to make 9. Adds to make -6. X minus 3. X minus 3. So what are the zeros? Okay, cool. Our zeros are x equals 0, x minus 3 equals 0, and x minus 3 equals 0, right? 1, 2, 3. That's going to be 0. That's going to be 3. And that's going to be 3. Right? And so we have this thing. These two are the same 0. We're crossing at 3 for both of these different zeros. So when it's saying what are the zeros and their multiplicity, what's really going on is that, you know, we could kind of erase this one. We could say that this has multiplicity 1 and this has multiplicity 2. Because there's 2 of these and there's 1 of these at 0. My fault. Now, if I want to graph this, and just to be clear, this is the same exact function, right? So I know I've got, you know, x equals 0 once, and I've got x equals 3 twice. So this is where we're kind of getting into a little bit of a paradox, a little bit into something that doesn't make as much sense, right? We kind of have 2 zeros and a degree 3. Now, I thought, Mr. Collier, if we had a degree 3, we would have an even number. And we do because we have this one twice. So we still have an even number of roots. It's just 0 and 3 and 3, which is weird because we've already said 3 once. But on the graph, that would be 0 and 3 and 3 again. And so there's our 2 intercepts that are really like our 3 intercepts. All right, we're back. Sorry, I got interrupted with a little bit of a phone call there. This is an odd positive function, which means our function should look like this, right? Should be going from low to high. And we need to play connect the dots now, right? We're going from low. Oh, come on, give me a blue color. Black's a little too boring for me. Going from low to high. We need to go through the first door and through the second door. And now all of a sudden we're stuck because we don't have a second door to go back through. We want to go through, but we don't have an x-intercept. And so how do we get back up here? Because we know we need to end up there. So what ends up happening is I like to imagine that this person right here is a person who is in charge of letting you in or out of an amusement park, right? And so imagine that this is the park, and this is the parking lot, right? And you've got out of your car, and you've gone up to this person, and you've said, "Hi, can I go through? Can I get into the amusement park? I have a ticket." And they say, "Sure," and you pay your 1 ticket, and you're able to pass through 0. So we go through, we get into the amusement park. Excellent, right? Now, let's do the same example again, right? We say, okay, there's the amusement park is now on this side. We're up in the parking lot, and we're trying to get in. And so we approach the person who's in charge of tickets, and we say, "Hey, can we go into the park?" And they say, "Sure, do you have a ticket?" And we say, "Yeah, we have a ticket." And so we go through, but then as soon as we go through, we say, "Wait a second, I've got another ticket. I've got 2 tickets." And they say, "Sure, well, you can go through again." And we end up on the top, okay? It's almost like you're trying to pay to go through a door, but you've got 2 tickets. You pay to go through, and then you pay to come right back through again. And so how this graph actually looks, rewinding through all of this ridiculous parking lot stuff that I've drawn, is that we go through, we say, okay, we have 1 ticket, so we pass. And then we get to this, where we have 2 zeros here, and we say that we pass through, but then we pass through again, and we end up on the top. Now, to be very clear, if we zoom in, we don't ever actually pass through the bottom, okay? What ends up happening actually is that we just basically turn around. But I think the double pay the ticket analogy works really well for students. Normally, if you're in class, I do a whole funny skit. It's not really that funny, where I walk out the door and I have these tickets and I pay to leave and I pay to come back and I do a bunch of, spinning myself around in a circle. But this is how our graph's going to look, okay? The bottom line is that if we have an even number of tickets, which are basically x-intercepts, we're not going to actually pass through the graph. Sorry, we're not going to actually pass through the x-intercept. We're going to be bouncing off the x-intercept. So let's look at this on Desmos. X cubed minus 6x squared plus 9x. X cubed minus 6x squared plus 9x. So here's exactly what we can see, right? We've got 1 intercept here. We've actually got 2 intercepts here. We've paid to go through, and then we've paid to go through, and then we've paid to come right back out. And we're going to end up staying on the top, but still touching this axis, right? So it's like here is a pass through. Here is a little bounce off, like a bouncing ball. Boing, we're going to bounce right off the intercept and not actually pass through it. So going back here, That was excellent. Very easy. So if your multiplicity of your roots, so what multiplicity is it's talking about how many copies of the root you have. Is odd, you're going to pass through at that 0. If the multiplicity is even, the graph is going to bounce off at that 0. So here's a through, here's a bounce off. Okay, cool. Now, to show this really simply, right? We've got an already factored version of our function, okay? It's got 3 roots, 1, 2, 3. We can find these roots from the factors, okay? So the first thing we need to do is take this x plus 7 and turn it into a 0 of negative 7. And it's a negative 7 because we take x plus 7 equals 0. We subtract the 7. Nice. Now this has a multiplicity of 2 because it's squared, because there's 2 of them. And that means that we've gone to the intercept, but then back through the intercept. And that means that we've done a bounce effect. Some people might, your teacher might have you write turn around or something, but I like bounce, whatever. This one is a little bit more tricky, but still very easy, very algebra 1. Subtract the 1, 2x equals negative 1, divide by 2, x equals negative 1/2. It's a fraction, but that's okay. How many of these do we have? Just one, right? There's not an exponent up there, so we have just one. And if you only have one, you're going to pass through. You just got one ticket into the store, so you're just going to pass through. And then this last one, we're going to have a 0 of a positive 4, and we've got 3 of them, right? So ask yourself, what happens if we have multiplicity 3? Well, you're going to pay to go through, turn around and come out, turn around again, and you're going to end up going through. Now, to be clear again, you don't actually look like that. You're basically just going to look like this. But that little hesitation there is the 3 different. That's kind of your character going, and ending up on this side as well. So remember, odds means you are passing through. Now let's do a little brief sketch of how this function would look, okay? We know that at negative 7, negative 1/2, and positive 4, we have intercepts. We know that we have a 1, 2, 3, 4, 5, 6. This would be a degree 6 function because we've got 1, 2, 3, 4, 5, 6. 6 different roots. And so we've got a degree 6 function, and we've got a positive degree 6 function because if we multiply these x's times these x's times these x's, it's all going to become a positive x, right? There's no negative out front. And so we've got an even positive. So that means we should look like this and this. So I get to negative 7, and I see that I have a multiplicity 2, and that I should bounce. And so I'm going to bounce off it. I get to multiplicity of negative 1/2, and I see we have a multiplicity of 1, so we're going through. See ya. And then I get to this last one, and we have this little hesitation move. We're going to look like that. And there's our function, okay? Same idea here. Just trying to go quickly. I don't think we need to slow down. I don't think we need to see Desmos again. I think you guys get it. This is not factored for us, so we could try to factor it, or we could just go to Desmos. And you know what? Let's just go to Desmos. Let's see x to the 4th minus 2x cubed. X to the 4th minus 2x cubed minus 8x squared. I don't know, something like that. X to the 4th minus 2x cubed minus 8x squared. Looks good. So here's our function. I see that we've got a intercept at negative 2, 0, and 4. So I can go ahead over here and plug those in. Negative 2, 0, 4. Looking at my multiplicity, looks like I've got odd here, even here, odd here. Because this is a bounce, so I know this is an even number of multiplicities. And I've got 4 total. So I need to have 1, 2, 3, 4. I need to have 2 here, 1 at each of those. And so it should look like this. 1, 2, 1, through, bounce, through. Feeling pretty easy. Lastly, we have a 0 at -6, multiplicity 2. 2, multiplicity 1. Write a polynomial function in standard form. So maybe instead of doing that, I'm not really interested in that. Let's go ahead and just look at the graph, okay? So I've got a 0 at -6. I've got a 0 at 2. This one means that we've got 1, 2, 3. 3 total roots means an odd function. And a polynomial function has a 0. Probably going to be odd positive because we don't hear anything about it being negative. And so it's going to look like this. -6 multiplicity 2 would be a bounce. That would be a through. And we're done. Okay? So 2 things that you need to kind of understand here. And it's basically this line here. That when the multiplicity is odd, you're going to pass through. When the multiplicity even, you're going to bounce off. And then up here at the top, that an even degree polynomial is going to have an even number of zeros. That an odd degree polynomial is going to have an odd number of zeros. That's it. That's all we need to talk about. Hopefully this helps.